As we did in the previous section, we consider convergent sequences of graphs along with associated sequences of graph filters. We showed that if the graph sequences converge towards a graphon, the graph filter sequence converges towards a graphon filter. But our statements are now in the node domain, not in the spectral domain. This convergence result provides our first approach to the transferability of graph filters. But the result is not useless either, because we can leverage it to prove convergence in the node domain. To do that, we have to go into the frequency domain and back. Namely, we begin with an input graph signal xn and compute its GFT to represent it in the GFT domain. We then process the GFT with the frequency representation of the graph filter, and come back to the node domain by applying the inverse GFT. Likewise, we get an input graphon signal x and compute its WFT to represent it in the WFT domain. We then process the WFT with the frequency representation of the graphon filter, and come back to the node domain by applying the inverse WFT. This is a promising strategy because we know that the frequency representations converge. The highlighted blocks are the same in the limit. However, the GFT and the inverse GFT do not converge to the WFT and inverse WFT. This proof strategy fails in general. Except, of course, when the signals are graphon band limited. In this case, the GFT and IGFT do converge to the WFT and IWFT. We have therefore just proved a theorem claiming the convergence of graph filters when given band-limited inputs. To state the theorem formally, consider a sequence of graph signals Gn, Xn. This input sequence generates a sequence of output graph signals Gn, Yn, in which each of the output signals Yn follows from application of the graph filter H of Sn. We also consider a graphon signal Wx. This input signal generates the output graphon signal Wy, in which Y follows from application of the graphon filter Th. The sequence of input graph signals Gn, Xn is convergent. It converges to the graphon signal Wx. The filters H of Sn and Th are generated by the same filter coefficients Hk. It then follows that if the input signals are C-band limited, the sequence of output graph signals converges to the output graphon signal. This theorem has been ready to prove, and it is also somewhat weak. Although we consider signals that technically have an increasing number of components, the signals are required to admit a representation on a finite number of components. Their spectral representations have a finite number of non-zero entries. A stronger result is desirable, and as it turns out, also possible. To do that, we introduce the notion of a Lipschitz graphon filter. The definition is what you would expect. A graphon filter is Lipschitz if its frequency response is Lipschitz in the interval -1, 1. That is, the absolute value of the difference between the filter's frequency response evaluated at lambda 1 and the filter's frequency response evaluated at lambda 2 is bounded by the absolute value of the difference between lambda 1 and lambda 2 scaled by a Lipschitz constant L. This condition must hold for any pair of variables in the -1, 1 interval. If we restrict our attention to filters that have Lipschitz frequency responses, we can claim convergence of the filter sequence even though we lack convergence of the GFT and IGFT sequences. Formally, we are given a sequence of input graph signals Gn, Xn that converges to the graphon signal Wx, along with filters H of Sn and Th that are generated by the same filter coefficients Hk. It then follows that if the filter coefficients are associated with a frequency response that is Lipschitz, the sequence of output graph signals converges to the output graphon signal. The proof of this result is not cheap. You can find the proof in lecture notes that are accessible through the course's website. We point out that the theorem does not impose restrictions on the input signals as we did when claiming convergence for C-band limited inputs. The restriction is on the type of filters that are admissible for the theorem to hold. They have to have a frequency response that is Lipschitz. The theorem is, not surprisingly, proven in the spectral domain. The first critical observation in the proof is that for GFT and WFT components that are associated with eigenvalues that are not close to zero, convergence is ready. This is actually our theorem for Bandlimited inputs. The challenge arises when we focus on the components that are associated with eigenvalues that are close to zero. We have seen that eigenvalues accumulate at zero, and that this causes complications with eigenvector convergence. It makes it impossible for us to claim uniform convergence. The second critical observation in the proof is to realize that the Lipschitz continuity hypothesis renders this problem void. Indeed, since the filter is not changing too quickly, all GFT or WFT components that are associated with eigenvalues close to zero are multiplied by a similar number. It doesn't matter that we can't tell them apart because the filter does not distinguish among them either. Look at the proof to see how these arguments play out. Aside from commenting on the proof, it is also important to comment on the implications of the theorem. A fundamental issue that we identify is that transferability is counter to discriminability. If the filter converges, it must be Lipschitz. If it is Lipschitz, its rate of variability is limited by the Lipschitz constant L. But as we approach lambda equals 0, we have closer eigenvalues, which means we would need thinner filters to tell components apart. But these thinner filters take longer to converge to the Graphon limit. Thus, we have wide filters that converge quickly to the Graphon limit. These filters transfer well but are not discriminative. Or we have thin filters that take a while to converge to the Graphon. These filters are discriminative, but they do not transfer well. The challenge is, not coincidentally, the same challenge we encountered in our stability analysis of graph filters. Also, not coincidentally, the challenge is inherent to graph filters. For as long as we use graph filters, transferability and discriminability are incompatible. The solution to this conundrum is, what else, to resort to the use of graph neural networks. Before we go there, we must contend with the weakness of our characterization. The result we provided is just a limit. We will work on transference bounds that hold for finite n.